All right, in the last portion of today's lecture, I'm going to discuss how we can get global policies from local models and local policies. So essentially, when we want to use simpler policies than neural nets, we kind of have three steps. We learn our local models, we get local policies from those local models, which is what we discussed in the previous part, and then we combine those local policies to get a global policy. And it turns out this idea of combining multiple local policies into a global policy is a very useful idea for model-based RL, but it's also a really good idea in many other settings beyond just model-based RL. So let's talk about that. The high-level idea is going to be this. Let's say that we have a particular task with some variability in the initial state. So maybe we have this robot and it needs to put this little shape in the shape sorting cube, kind of like the Lego task that I showed before, but the object can be in different locations and the robot doesn't know where the object is, so maybe it has to use vision to figure out where it is. What we can do is we can learn a separate local policy for each of these situations. So we learn one local policy when it's over here, one local policy when it's over there, one local policy when it's over there. And each of those could use the LQR-FLM method from the previous section. So that's kind of what this would look like. And then what we would do is we would collect all the data from these controllers and use that data as essentially expert data with supervised learning. So we would essentially treat these local policies as demonstrations and then imitate those local policies with one global policy, which could now be represented by a deep neural net, and it could even use vision to choose actions. So that would look maybe something like this. So now regardless of where you put the object, the robot can look at the image and figure out where it is. So a basic sketch of the algorithm would look something like this. You optimize each local policy, which I'm going to call PyLQRI, where I indexes the local solutions. And that local policy starts from initial state x0i. And you would optimize it with respect to a modified cost, CKI. K indexes the iterations, I indexes the initial states. And the cost that you use is modified to include the task reward and an additional term to keep PyLQR close to the global policy PyTheta. Because you don't want PyLQR to take actions that are different from the actions PyTheta would take. If all the different local solutions do very different things, if they disagree, they might be difficult to synthesize into a single PyTheta. And then you use the samples from step 1 to train your global policy PyTheta with supervised learning to mimic all of the PyLQR solutions together. And then you would update your cost function with an additional term for each of the local solutions that keeps them close to PyTheta. So you would add log PyTheta times some Lagrange multiplier. And this could be treated as enforcing a KL divergence constraint. So this is a Lagrange multiplier. And then repeat this process. So repeating this process every step of the way, each PyLQR would improve because it's taking one more step of that LQR-FLM algorithm. The PyTheta would improve because it's being supervised with more good data. And the PyLQR solutions would learn to stay closer to PyTheta because the constraint term is being added to their costs, C tilde. So that's the basic sketch of the guided policy search algorithm. The principle behind the algorithm is that it's easier to construct these local solutions using simple and scalable methods, and then synthesize those solutions together into a global policy. If you want to see more details about this, check out the paper End-to-End Training of Deep Visuomotor Policies. I went through this pretty fast because I mostly just wanted to provide a sketch of this method. But underlying this method, the basic principle, and this is actually something that came out subsequent to the guided policy search work, but I think this principle explains the idea fairly well, is something that has come to be known as distillation. So the idea in distillation is that if you have an ensemble of models, that's a good thing. So single models are often not the most robust solution. Instead, if you train many models and average their predictions, then you get a better, more reliable solution. And this is how a lot of ML competitions, like for example, Calorie competitions, are won. This slide, by the way, is borrowed from Jeff Hinton when he described distillation. The trouble is that lots of keeping all those little models around can be very expensive at test time. In the case of RL, you have to select which model to use, but even if you have an ensemble, just keeping them around can be very costly. So can you instead make a single model that's as good as all of your models together? In the realm of supervised learning, when we talk about model ensembles and things like that, and image classification, what you could do is you could essentially train a single model that's as good as your ensemble. So you can use your ensemble to produce soft targets, basically ask it for probabilities on all the samples, and then train your single global model with those targets as the ground truth labels. So you have soft labels. And for example, if your ensemble makes predictions logit zi, then you scale them by some temperature T and treat those as the probability that that label is the right answer. So the intuition is that this ensemble has more knowledge in these soft targets than it does in the hard labels. In supervised learning for image classification, one good example to illustrate this is if you consider MNIST digit classification. So these are the MNIST digits, 0 through 9, and the ground truth digits are labeled with their true label. So it's just a one-hot vector for 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But if you look at some of the 2's, like if you look at, for example, some of the 2's that are on the right side, the rightmost 2, it looks kind of like maybe an 8 or a backward 6. So you might expect that your ensemble might say, well, it's like 80% likely to be a 2, but maybe it's 15% likely to be an 8 and 5% likely to be a 6. Now those labels are less correct, but they contain a lot of knowledge. They contain the knowledge that 8s and 6s look a little bit like this shape. So by training your global model with those soft targets, you're conveying that knowledge to your global model. You can think of what guided policy search is doing as also a kind of distillation process. The difference is that this distillation process isn't aiming to take a smarter model and encapsulate the knowledge of that smarter model in a simpler model. Instead, it's taking heterogeneous models that model different parts of the initial state distribution, and synthesize them into one model that succeeds at all those initial states. This basic idea can be used in model-based RL as I described, but it can also be used more broadly. So there's been quite a bit of work on distillation, for example, for multitask transfer. You could train policies for many different tasks individually. So maybe you train one policy to play Space Invaders, one policy to play Breakout, one policy to play Pong. You can train all those individually, which is fairly easy, and you can do it using even the algorithm that you're implementing for homework 3, and then use it to produce expert data, which you can then synthesize to train a single central policy that emulates the behavior of all of these local policies together and can therefore play lots of different Atari games. This is basically the same principle as in guided policy search, except that now those local policies might not be trained with model-based RL, they could be trained with other model-free RL algorithms. So if you want to check out more about this, check out the paper at the bottom of this slide called Actor Mimic, Deep Multitask and Transfer Reinforcement Learning. So the idea is your expert, the Pi AMN, the one that is playing all the games, is just going to run supervised learning on actions sampled from all of your individual local policies. So this is analogous to guided policy search, but aimed at multitask learning and using model-free learning as the underlying algorithm. You could also combine multiple weak policies into a strong policy learned with model-free RL, but with local neural net policies instead of local time-varying linear policies. So you can do the same kind of decomposition over different initial states, and then run supervised learning with the KL divergence constraints. This is an algorithm called divide and conquer reinforcement learning. So the sketch for this algorithm is you optimize each local policy pi theta I on initial state S0i with respect to your modified reward. You use the samples from step 1 to train your global policy pi theta, and then update your reward function the same way as in guided policy search to add a log pi theta term to enforce a constraint. And then repeat this process. So to learn more about this, check out the paper Divide and Conquer Reinforcement Learning, and here is kind of an illustration of the basic algorithm. So here we have a standard TRPO algorithm like the one that I covered in the Advanced Policy Gradients lecture trying to catch a ball, and you can see that it kind of does okay for many different positions, but doesn't actually succeed consistently in any one. But if we train catching policies individually for different positions and then combine them into a global policy, then it can catch the ball from any angle reliably. Okay, if you want to learn more about these general ideas, here are the papers that I covered. End-to-end training of deep visiomotor policies describes sort of the model-based RL version of guided policy search. Policy distillation and actor mimic describe this idea for multitask learning. Divide and conquer RL implements the constraint and essentially extends guided policy search to use model-free local policies. And then Distral is another paper that's kind of concurrent that does basically the same thing. Okay, so that's it for model-based reinforcement learning. Next week, we're going to cover variational inference in more detail, and then talk about how we can view optimal control and reinforcement learning as an inference problem, which will give us an interesting perspective on these algorithms and lead to lots of new additional techniques.